Can you hear me? So, check. Okay. So thanks for the organizer to come with this very nice lineup today and for giving me the opportunity to present our work. So I'm Matthieu GILSON. I'm a computational neuroscientist at the INT and Aix-Marseille University. And so together with our colleagues from CRMBM and also which are Aude-Marie Grapron and Wafa Zahari in particular, we initiated this dataset collection on 7 Tesla MRI on ALS patients. So I'm going to present you how we can use this data for prediction of the evolution of the patients. So I will start with presenting the cohort, which is a small cohort. So as you may know, it's quite difficult to put patients in an MRI scanner. So it's a slow acquisition process, but so far we've got 21 patients that have been acquired on the 7 Tesla MRI. But today I'm going to present the analysis that's been done on 16 of these patients. And so we've got 14 match controls. And so these patients have been evaluated in using the ALS FRS score. And from that, we could divide the evolution of the patient into two categories. So those where the ALS FRS score would evolve faster. And so that's a group of fast evolving patients as compared to patients who evolve more slowly. So the point is to discriminate between these two categories of patients. And we are going to use machine learning techniques to try to discriminate the three classes, so control, slow patient, and fast patient. And of course, for the clinical relevance of that is to identify the fast evolving patients, which are the ones for which we need to maybe be more quick to organize treatment or also. So the 7 Tesla MRI data that you acquired has several modalities. So structural MRI is the classical MRI used in hospitals. And this is not informative about ALS disease. So in addition to that, we acquired quantitative T1 and also diffusion tensor imaging. So several measures related to this. So that's another type of measurements. And sodium MRI on the right is a novel technique, so more advanced technique that's looking at the concentration of sodium in the neuronal tissue in the brain. And so why we do that is because where you've got structural MRI like T1 more quantifying the structure of the neuronal tissue, the DTI, diffusion tensor MRI, is more concerned with the microstructure, so more finer level of possible alteration of the neuronal tissue. And last, the sodium MRI itself is more concerned with the metabolism of the neurons in the brain tissue. So the idea here is that by looking at the metabolism and having quantitative measures of this, we could see alteration that may come before the cellular death of the neurons that would be reflected in the microstructure and then the structure. So by incorporating in our prediction pipeline sodium MRI, we aim to be able to have earlier markers for the prognostic of the evolution. So the first part was to pre-process the data. So here's an example of a patient's data. We then use FreeSurfer, which is a usual tool, to divide our brain in a number of regions. And so here we can divide the brain into several parcels, as it's called, not only for the gray matter, so the cortex, but also importantly the white matter, because it's known that white matter is important for the evolution of ALS. And what you end up is in 3 dimensions, some region of interest, so RI, where you can measure for each modality the value of your measure in the different voxels, or different parts, different pixels of this region. And so you end up with a distribution, and you can calculate, for example, the mean there, and check whether, and this will be the representative value for your region. So one new recent improvement that we went was using some technique from data analysis specific to neuroimaging, that is error erodation, which aims to remove outliers in this distribution here and try to get a better representative value for our region. So I'll come back to that later to show you the improvement of incorporating this in our prediction pipeline. So if you take one modality, so we've got our 30 patients here, and you've got our region here on the x-axis. So you've got 332 regions for this example with gray matter and white matter. And what we have is, for each patient, we've got our label, which is either a control or slow evolving patient or fast evolving patient. So in orange, lighter and darker here. And we are using usual cross-validation scheme in machine learning, which is the leave one out, meaning we are going to train our classifier with all the data except for one subject, and we're going to test whether this subject is correctly predicted. Now, with this, we've got performance, so an accuracy of the prediction, and we want to have a baseline reference for that. So for this, we're going to do label shuffling, retrain our classifier, and that will give us distribution. So we can do this permutation several times, retrain and get the accuracy. And we've got a distribution, or what we call chance level accuracy, which is our baseline reference. Okay. So in a sense, this green distribution is what you get when you train your classifier with noise. So there is no information there. And the red point is what you get with the data. And so the idea is that if you've got good accuracy, and so that means you're getting close to 100% of prediction, that's good. But we can get a measure of the confidence in our prediction by seeing how the red point is separated from the chance level distribution. So that's a measure of confidence, and that's quite important because we've got a small number of subjects in our data. So we can do this for one modality of fMRI, like quantitative T1. We can do it for our 9 modalities, including DTI and sodium MRI for the different measures. And the question arises how to best combine these different modalities for the prediction. So for this, we use algorithm and pipeline, for data fusion. It's all automatized, and that was the work done by Shailesh Apukutan, which was our postdoc, hired thanks in particular to the funding by ARSLA. And so we recently published a paper that really tested in depth pipeline and many variations of the pipeline, so 1,800 configuration, where we have all sorts of steps for selecting the data, preparing the data, selecting the best data for the prediction, testing different classifiers, and their parameterization. So it was maybe an overkill for this data set, but why we did that is because there is a bias in the computer science community or data science community, which is that you can get the best from any data set, provided you get the good classifier. And so here, what we wanted to test is really making the contribution of the data and of the classifier to the prediction. And what we found is that, of course, because we've got limited data, simple classifier work rather well. But we could really test the ability of each of these steps in this configuration. And long story short, so as I said, we are going to classify the 3 classes, control versus slow and fast patients. And the first thing that you highlighted is that if you use the gray matter, you've got not too bad classification accuracy, but still close to the chance level. If you use gray and white matter, then you've got better accuracy and you're making much better than the chance level. So that's one point. And so the latest improvement was with the region erodation, so ROI erodation that I mentioned. And so when we do this, then we jump from another 13%, from 70 to 83 here. And we are further away from the chance level. So complementary to what I said just before, preparing the data well is more crucial in this case than just tuning the classifiers. Okay. So last part is focusing on the separation between slow patients and fast patients. So here you've got what's called the confusion matrix. And so because we have control, patient, and slow and fast, here you can see where you're making errors. So here on the x-axis, you've got the prediction of the best model. And you can see that if you ignore the controls, we can look at the prediction for slow patients here. And we are making errors. One patient has been classified as fast, and 2 patients slow has been classified as control. But of course, we know that patients are patients and controls are controls. And what we found is that if we group together controls and patients here, we can still have a very good discrimination between fast and slow patients with just 2 errors on our data set. And so this is done when we do the classification using the control. And if we had done that without the control, we would have this picture here, where we still get good classification accuracy, but we are still in the chance level. So meaning we've got even fewer data here, fewer subjects, fewer patients to use. And so that means that this level of accuracy could be achieved by chance randomly. Okay. So it's important to use controls in this. And here's a summary of different predictions using the different modalities. And you can see that they all contribute differently to the prediction of the patient. And so that justifies why we need to combine them to make the best prediction possible. And following, what you can do is identifying the best, the most informative features. So trying to see where we have information to make the prediction. So we can look at that for the different modalities, of course. And just as a reminder, so if you were doing statistical testing, so if like our medical doctor ordinary would tell us, okay, I think this part of the white matter is interesting to check for this modality, like sodium concentration. So we can test the statistical power individually of each person and make a statistical test for that. But if you look at the p-value, they are barely informative alone. So we really need to combine all the different features to make robust prediction. And so within that, we identify a number of regions and related modalities that are informative. So we see a lot of sodium MRI measures for the white matter, but also, and maybe more surprisingly, cortical regions with the DTI measures. So, of course, this is preliminary and should be taken carefully, but the point is that to discriminate the slow and fast patients, we think that we need to also take part into the cortex, which was not obvious at the start of the study, at least from the clinician viewpoint. So to summarize, we've got results that show that white matter is important for the classification accuracy, that we found some best modalities from MRI for the discrimination. And we've got some hopes using this pipeline that we can separate patients with fast progression from those with slow progression. So that's, of course, work in progress. And we know that in clinical practice, it may not be easy to put all the patients in MRI scanners, especially 7 Tesla MRI scanners. But that may give us some ideas about where to look at, maybe for different techniques. So where things are happening to discriminate these two categories of patients. And so the next step, we want to refine our pipeline, in particular for the data preparation, so testing different parcellation, different ways to separate or to divide the brain into parcels, into regions. We are going to include recently acquired patients. So now we've got 21 patients and same number of controls. We also have 3 Tesla data, so earlier data that we want to put, and there we will have to do data alignment because we've got different scanners there. And we also have functional MRI and structural connectivity that we get from the DTI that may be also interesting to put in the pipeline. And with Ksenia Gobeleva from the University of Bochum, we also have further functional MRI data that are tasks. So patients were put in the scanner doing some tasks. We want to see whether this can also contribute to correct prediction. And the last part would be to improve the data fusion, which is quite basic, so I can talk about that if you're curious. That's what I wanted to present you today about our work. And so if you want to refer to the publication, that's here. And we want to thank the ARSLA Association, of course, for the funding, and also the Laennec Institute from Aix-Marseille University. Got this. And this is the whole team that contributed to this work. And with this, I thank you for your attention.
We have time for 2 or 3 questions.
Thank you for the talk. How did you take into account the confounders for disease progression, such as age at onset, site of onset, eventually sex also?
Yeah, so we don't have a strong control on that, but we've got different onset sites for the 16 patients so far. So I mentioned roughly 40% of lower limb and 40% upper limb, and also 2 bulbar onset. So with this, we've got diversity in the patient, so to say. So of course, if you want to have stronger control, in particular with the age, we would have to get more data to have the matching between the 2 groups of patients. So far, we just have the matching with the control and the patient together. So that's of course something that needs to be addressed. And for that, there are some cohorts that also exist in Canada. We've got some of them, ICTALS and things like that. So we want to bring more data, align them, and try to test. And with more data, we can do this control. So far, we're limited. It's all in the data in this.
Good morning. Thank you for your talk. I had a method question about your sodium imaging. How do you analyze it? And is it like, for example, less sodium in your extracellular medium, meaning that you have more activity, or not at all? Thank you.
Okay, so the sodium that you see here is like the total concentration of sodium. So when you put when you get the signal of the sodium relaxation in the scanner, you actually have several time constants, which are called here long and short relaxation time, and they would be affected by the different property of the sodium. So sodium that would be intracellular or extracellular, this kind of thing, so bound to some compound or free. So this kind of this time constant, they quantify some properties of the sodium beyond the total concentration that you have got there. So with this, that's more a matter of interpretability, but so far we're just taking all of them together in the pipeline. And for this, I would refer you to Wafa Zahrawi, who's the real expert in sodium MRI. Now, the second part of the question was about. Sorry, can you?
Extracellular concentration.
So you've got part that is linked to the extracellular concentration, but it's reflected differently in this constant. So yes, for that I am not sodium MRI expert myself, so I would refer you to the work of Wafa Azari, who has looked at that very carefully.
Okay, thank you.
Thank you very much.
Thank you.
So next is Claire Kissar from CHU de Nîmes. We're going to talk about RNA-seq approach for molecular diagnosis of ALS.